discussing electric potential and then capacitor, charge holding capacity, SI unit of capacitance. Now we are going to extend the effect of dielectric on capacitor, also the behavior of dielectric in an external field. Let us see this one. It's a electric potential. Conductor, insulator, we have discussed. Conductors have free charges and therefore the electricity can flow through them. Insulators, there are no free charges, so no electricity can move or no electricity can pass through it. But dielectrics, what are the dielectrics? Dielectrics are basically insulators. Here, dielectrics are insulators, non-conductors. These are non-conductors, we cannot say it's insulators, or even we can use it. Dielectrics are basically insulators. But then what difference is there in insulator and dielectric? That we are going to study here. Let's see first, we have already discussed this one, but once again we will discuss behavior of conductor in an electric field. There is behavior of conductor. This is conductor, capsule shape we are taking it. This is electric field going from here to here. Electric field is going from here to here. What does it mean? E is here. It simply means positive plate is here and then negative plate is here. So between these two plates, electric field is going from here to here. Whenever uniform electric field is created, it is because of charges on the plate. Now, it's a simple way to create external electric field. Now, conductor, we all know there are three charges. E external, this is E out. We can say that. Now, because of these positive plates, negative charges start drifting towards this side and positive charges start drifting towards this side. Now you can see that inside the conductor, this side became positive, this side became negative. Therefore, inside conductor there is E in. This is outside. So inside conductor, because of movement of charges, electric field is developed. And this one goes on happening when, as long as equilibrium does not exist. See that. What does it mean? Here, this positive, negative charges will keep on coming here. But as soon as this E plus E in is equal to 0, addition of these two becomes 0, then no negative charge will drift towards this one. It means that E is equal to minus E in. Inside the conductor, the field opposite to the external electric field develops due to the movement of positive and negative charges, or even we can say that separation of positive and negative charges, and this keeps on happening. Still, both the fields are equal. They are already opposite in direction. So this is the situation in conductor. But let us see what happens in dielectrics. In dielectrics, this is not the situation. Again, I am taking, this is a dielectric. This is electric field here. You all know now, I am not showing it here parallel plates. Or even we can take it, this is the positive plate. This is negative plate. In this dielectric, what happens? E out is there in this one. Now, charges are not free to move, but the charges can separate slightly inside the atomic level. See this one. Here what happens? There is minus and plus separation happens. This charge cannot go from one place to another place, but inside the atom this separation takes place, and then there is a slide E in develops. But in case of dielectrics, E in addition of these two is not equal to 0. Here addition of these two becomes 0. Here addition of these two does not equal to 0. This is not equal to this one. Polarization takes place, but not to the extent that it cancels out external electric field. This is the basic difference between dielectric and conductor. This is happening because of this type of slight separation between charges at atomic level. And this one, this is called as polarization. What is called this one? This is known as polarization. Polarization is the dipole moment per unit volume. See that. As soon as this happens, there is a dipole moment. So what is the polarization? Polarization is defined as dipole moment per unit volume. P is denoted by P. It means that dipole moment is always given by, it indicates dipole moment is equal to polarization into delta V. Delta V is a small volume. In this one, there is a slight separation takes place, but there is a dipole moment in this slight volume, but net charge on this one is 0. Let us see how this happens, or origin of this one. Basic elements, if you check it, they are classified into two types of substances. One is called as non-polar substance and one is called as polar substance. What is meaning of non-polar? Non-polar. We all know there is a nucleus, positive charge. There are many positive charges, proton, and they have one center of mass, which is also called as center of positive charge. There are electrons around this one. Many electrons, they have their center of mass, that is called as negative charge center. So at atomic level, there are two centers. One is called as positive charge center. One is called as negative charge center. When positive charge center is at the same place where the negative charge center situates, this is called as non-polar substance. So non-polar substance is defined as the substances for which positive charge center and negative charge center overlap. They are not separate from each other. All symmetric molecules are non-polar substances. Hydrogen, oxygen, these are known as non-polar substances. At atomic level, there is no dipole moment in case of non-polar substances. But what about polar substances? What happens to the polar substances? In case of polar substances, the positive charge center is not. There is a positive charge center, there is a negative charge center, and there is a dipole moment at atomic level itself. In case of polar substances, positive charge center does not overlap negative charge center, and there is a slight dipole inside the substance itself. So these substances are known as polar substances, polar substances, all asymmetric, H2O, water molecule or carbon dioxide, these all are asymmetric substances. They are polar type of substances. Now what happens to them in electric field? Whenever electric field is applied, this is plus, this is minus, and then these are plus minus. I am talking about non-polar. So all this non-polar, they don't have, these are not having any dipole moment. E is equal to 0. Field is 0. No dipole moment. This is what? Non-polar I am talking. Now let us see what about polar. This is plus E. This is I am talking about polar. Minus. If E is 0, then there is no field. E is equal to 0 means it is no field. Then all these 1, minus plus, minus plus, minus plus, minus plus, total dipole is 0. It does not cancel out at atomic level. It cancels out at a substance level. Because of random thermal agitation, all molecules are oriented in such a way that net dipole moment is 0 in absence of field. Now as soon as field is applied to this polar R, what happens to the polar? Polar slightly, this polar as soon as this is applied, polar gets, this is plus plate, this is minus plate, this is minus, this is plus. So they align themselves, dipole moment align themselves with the field, and there is a net dipole moment in case of polar when slight field is applied. When slight field is applied, they get slight dipole moment. But this is not in case of non-polar substances. Now, these are the effect of electric field on this one. We also define one more thing, linear isotropic dielectric. What is the definition? Polarization already I have defined. What is the polarization? You can see this one. Polarization is defined as dipole moment per unit volume. Now this polarization is directly proportional to applied electric field. This is also equal to Xi E. This Xi E is called as susceptibility of material. This is known as susceptibility of material. It is Xi E. Now we are defining one more thing, which is called as linear isotropic dielectric. What is the meaning of linear isotropic dielectric? Second definition we are doing here. Linear isotropic dielectric. What does it mean? We know this is the field. Positive plate here. Outside I am showing it. This is minus here. Then, if it goes in this way. So P is, dipole moment is always from negative charge to the positive charge. Whenever dipole moment is developed, this one is, the dipole moment is from here to here. Now field is also from here to here. So the substance is said to be linear isotropic dielectric, in case of which the dipole moment is along the electric field and the amount of polarization is dependent on the field strength. Two factors I am seeing. Dipole moment is along the field direction, and the amount of dipole moment or amount of polarization is directly proportional to electric field. Such type of substances we call it as linear isotropic dielectrics. Now this polarization again depends upon two factors. One is potential energy of the electric dipole. So potential energy of the dipole, and second, it depends upon the agitation due to temperature, thermal agitation. Both are mutually opposite to each other. That is, the potential energy of the dipole is disturbed by the thermal agitation of the substance. But this polarization, it depends upon these two things. Now, how it affects? Suppose that we take slab of one dielectric. In such case, suppose that we are taking slab of dielectric. What happens? What is the effect of? There is parallel. We are taking it. It's again a slab of dielectric. Plates. This is plus plate. This is minus plate. Now, this will come. This will come. This will come. Same thing happens about top. This all gets aligned to this plate. Now you can see this much part. This neutralizes this one. This neutralizes this one. Therefore, here there is no fit. Because of this type of separation, because of this type of just positive and negative polarization, then if I remove this one, I get it here. It's a positive plate to this side. Slight negative charges are coming. These are not equal. There is similarly, here it is a negative plate and slight positive charges are coming. What does it mean? Electric field from here to here, and then there is field due to polarization, sigma p. If you check this one, there is slight decrease in electric field. So this EP due to polarization will say. So net force inside this one is net is E, this one net E minus EP, which is equal to, it develops surface charge density sigma minus sigma P divided by epsilon C. We know that because of any charged conductor, this is electric field is surface charge density divided by epsilon 0. So surface charge density reduces. This is the effect of dielectric inside two parallel plates. Now what way it affects the capacitor? Effect of the effect of dielectric on capacitance. What is the effect of dielectric on capacitance? Let us consider Q is a charge on one plate and minus Q is a charge on other plate. A is area, D is a distance of separation, and C is a capacitance of capacitor. Therefore, we all know E is equal to sigma divided by epsilon C. Therefore, B is equal to E into D, which is sigma epsilon 0 D. We can say by A. So B is equal to Q D epsilon 0 A. From this one we get it Q by V is equal to epsilon 0 AB, which is nothing but capacitance when there is a vacuum or air between two plates. This is C0, capacitance when there is a vacuum or air between two plates. Now suppose that it is replaced by some dielectric. In this one we placed some dielectric. Because of this one there is a plus charge, there is some minus charge. There is a plus charge, there is some minus charge. And then the sigma, it becomes sigma minus sigma P. The net surface charge density becomes sigma minus sigma P. Therefore, E is equal to sigma minus sigma P divided by epsilon 0. Now, this sigma minus B is equal to, this is B is equal to E into D. Therefore, B is equal to sigma minus sigma P epsilon 0 D. But sigma minus sigma P is proportional to sigma. Therefore, sigma minus sigma P is equal to sigma by K, where this is called as a dielectric constant. This one is known as dielectric constant. So we get it as V is equal to sigma divided by K epsilon 0 into D. Again this we can write it as A K epsilon 0 into D, and from this one Q by V is equal to A K epsilon 0. This is nothing but it's a capacitance after introducing dielectric stack. Here we introduced dielectric stack. If you take ratio of these two, C by C0, if you are taking it, or C0 by C, you can take it. C by C0 is equal to A epsilon 0 D into D A epsilon 0, which becomes K. So this is nothing but it's a dielectric. We have defined this dielectric in first chapter. We know that K is nothing but it is the ratio of permittivity in space to the permittivity in free space. K is equal to. But on similar line, we know that F is equal to 1 upon 4 pi epsilon 0 Q1 Q2 divided by R square. F0 we have. Similarly, F in any medium 1 upon 4 pi epsilon 0 Q1 Q2 divided by R square. So here it becomes epsilon. When I am taking ratio of F0 by F, F0 by F, it becomes epsilon divided by epsilon 0. So it is the force between two charges, ratio of force between two charges in free space to the force between two charges in dielectric. Similar line we can define E0 is equal to 1 upon 4 pi epsilon 0 Q by R square. E is equal to 1 upon 4 pi epsilon 0 epsilon Q by R square. So E0 by E is equal to, if you check it, there are three ways to define this K. K is equal to epsilon divided by epsilon 0 F divided by F or E0 by E. So this is the dielectric constant. Dielectric constant is greater than 1. Therefore, this capacitance of the capacitor increases when the dielectric is inserted between it, and this is the effect of that one. This is the effect of dielectric on the capacitance. Now let us move to the next one, that is relation between psi and k. This is the relation between susceptibility and dielectric constant. We are going to discuss the relation between susceptibility and dielectric constant. Let's see what is the relation. Relation between psi e, k and epsilon e. We know polarization is equal to sigma p is equal to p dot n. It is density due to polarization and p is the polarization. We know this one. Now electric field E is equal to sigma minus sigma p divided by epsilon 0. In vector form we can write it as sigma minus p dot n divided by epsilon 0. Therefore we write it as epsilon 0 E dot n sigma minus p dot n. It's a unit vector normal to the surface. Now we get it sigma E dot n plus p dot n is equal to n cap is common plus p dot n is equal to sigma, or sigma is equal to d dot n. This is called as displacement of dielectric. D is called as displacement of dielectric, which is D is equal to sigma E plus P. D is equal to sigma E plus P. Now we can take ratio of D by E. We know E is equal to, that is, it becomes minus sigma p epsilon. D is equal to, because D is equal to what? D dot n is equal to sigma from this one. E is equal to, E dot n is equal to sigma minus sigma p divided by epsilon 0. When we are taking D by E, it becomes sigma minus p epsilon 0. This is coming your relation. D is by dt is equal to sigma divided by sigma minus sigma p epsilon 0. Now D we can write it. D is equal to what? D is equal to, here it is coming, epsilon 0 E plus P. It is a T. This is by E. Overall, if you check this one, this is coming as final relation sigma minus sigma p, which is sigma divided by sigma p divided by epsilon. Permittivity is a coming. Now, can you see this one? This is coming as k epsilon 0. This one is coming as k epsilon 0 e plus p, which is equal to k epsilon 0 e. This side we get it. P is equal to k epsilon 0. P is equal to epsilon k epsilon 0 e minus epsilon 0 e. Epsilon 0 e is constant, k minus 1. Already we have seen this is P is equal to xi p into E. Comparing this to xi p is equal to epsilon 0 k minus 1. This is the relation between xi, which is equal to epsilon 0 k minus 1. That's all for this topic. Thank you.